go ahead and get started here. See if this will work. So I put part one here because there might be a part two coming up. And we'll talk a little bit more about how to analyze your data and stuff. But I won't be talking about that today. Did you guys all get a discussion on NFC and 248? At least have an introduction to this? No, yes. A little bit, okay. So hopefully, we're expanding on what you got in 248. So I'll talk a little bit about, what is nanocellulose, what makes it. We'll talk a little bit about history first, the characteristics of nanocellulose, and how it's used in the world, right? I imagine there's probably a lot of things that it's used in that you're not even aware of. Then we'll talk briefly about the oxidation chemistry, specifically the green chemistry that you'll be using to make NFC. I'll talk about the pathways, the reaction pathway that's specific to this chemistry. And I want to talk a little bit about what this chemistry is doing to the surface of the nanocellulose, so how it's activating it. Then we'll talk about specifically the process conditions that you guys will be interested in and the response equations that you'll use to produce it. Part two, we'll talk more about how to interpret your results. Okay. All right, so everybody knows when cellulose was invented, right? 470 million years ago during the, I cannot pronounce that, Ordovician period, right? Everybody knew that, didn't they? And it took 70 million years before trees were invented. That was kind of the climax and the height, the development of cellulose, right? During the Devonian period. Now I'm going to call the next 400 million years the dark ages of cellulose development, even though a paper was made during that time, right? We're focused today on just nanofibrillate cellulose. Cellulose on the nanoscale, we didn't see the first production of it until nanocrystals were produced in 1949 by a person named Ranby. And even then, nano was not in the lexicon, right? It wasn't until 1983 that at ITT Rainier, and Mike might correct me, but I believe Mike actually worked at Rainier. I'm not sure he worked in their research group, but for some reason, I think he may have worked with those guys. So they had a big research facility in South Carolina, and that's the first use of the term nanocellulose. And they made nanofibrillate cellulose for the first time. Now, you'll see that there's a gap in my timeline. During the next 30 to 40 years, it wasn't that the research stopped. There was a tremendous amount of research in it, and it climbed quite fast in developing crystalline nanocellulose, looking at different chemical and mechanical methods, just a real explosion of work. What I want to highlight is that there was a large period of time from beaker chemistry to the point at which folks were actually making it in larger quantities. In 2008, in Finland, VTT started the first center that was focused on specifically nanocellulose. So I just want to kind of highlight that. There was lots of independent work up to this point, but this was the first concerted effort. A company called Inventia followed suit a few years later and started their first pilot plant using a mechanical means. They were only producing 100 kilos a day, right? Shortly thereafter, in 2012, U.S. Forest Products, one of my old professors, Dr. Alan Rudy, started up a nanocellulose pilot plant, and they produce nanocellulose. They have a bunch of different reactors. I believe they do with tempo, and I think they may use sulfuric acid. I believe that and Renati, I think you're familiar with this one. I think it's in Wisconsin. Is that correct? I can't remember where it's at.
It is.
$1.7 million gives you a really cool lab. The University of Maine that same year started up their nanomaterials pilot plant, and so they produce crystal nanocellulose and NFC using mechanical and chemical means. SAPI is a South African company, I believe, and they funded a plant in the Netherlands as well in 2015. And then Paper Logic in Turner Falls, Massachusetts, has started the largest one to date at 2,000 kilos per day. So I'm sure you're all thinking, oh, so what? 2,000 kilos sounds like a lot. If you compare it to one of the smallest pulp mills in the Northwest here, they produce 400 metric tons of pulp a day. So 2,000 kilos isn't much. Can anybody guess what the value of 1 gram of nanofibrillated cellulose or CNC is on the open market today?
$100.
100?
Yeah, maybe.
Okay, you're not out of the ballpark. How much is gold right now?
1,200 an ounce or something.
So we're going to do the metric system because I don't think in ounces. It's $57 per gram as of this morning. So nanofibrillated cellulose, just to put it in perspective, because why has there been this big explosion? It is being sold right now for $25 to $35 a gram. It depends on how it's made. So if you're the consumer, depending on what you request, it only goes up in value. So it's almost the price of gold. So it has a lot of, so 2,000 kilograms per day is actually substantial, okay, when you put it in terms of cost. I'm not going to talk about the environmental aspects of nanofibrillated cells. I think you guys have gone on that, but I don't want you to lose sight of that. And perhaps I'll talk about that in the next part too, a little bit more.
If I can add
Yeah.
something to it. So remember, it is always running joke in 406, unless you're making diamonds out of the biomass, you can do certain things in terms of buying more expensive equipment, having many stages of your process. I'm talking about capital operating costs and affording a more expensive biomass, right? So I know you're not making diamonds, but you're making half gold, whatever it is. Just so this is, I'm so glad Kurt, you just, compared the prices. So you can imagine why, if you see certain processes and you see we're going to be using lots of electricity, a huge amount of electricity, energy to get this stuff into nano level, because the product is so expensive, right? So this is, in 406, we talked about always, cheap or a little bit more expensive products. They're chemicals, right? Now, I'm not saying sky is the limit, but you see the final product is really expensive. So you have more, obviously, opportunities to use different equipment, and you don't have to worry as much as if you produce a large volume, but very inexpensive product. Right now, you're producing a very small volume, but expensive product, right? So it's a completely different situation. That's why, Kurt is working on it. We are working on it. Many groups are working on it, because you can actually afford to come up with different solutions in terms of technical technical solutions in terms of operating capital cost, and you still can make money out of it at the end of the day. And if you're making ethanol from biomass, lignocellulosic biomass, I'm not saying from corn, this cannot be, it cannot happen because it's too expensive, right? So I just want to make sure we're not talking about completely different products, and that's why it opens many doors as you never seen this before. Okay.
Yeah, you guys are going to be spinning wheat straw into almost gold. All right. So nanofibers, this is one of my pet peeves in all the literature that you read. You think that after 40 years, people would have agreed on what acronyms to use. So when you guys do your literature review, you'll see references to cellulose nanofibers, or CNFs. You hear me talk nanofibrillated cellulose, NFCs, crystalline nanocellulose, CNCs, and then microfibrillated cellulose, MFCs. And if you read enough articles, you'll find people interchanging these all across the board. I use NFC because I don't want to be confused with CNC. To me, CNF and CNC sound too much alike. But what's really important is when you read the papers, it doesn't really matter what they're calling it, as long as they communicate to you in the paper what is their diameter and length, because that's really what determines the differences and delineates between all these materials. So I've got this table here. You see the abbreviation NFC, CNF, nanofibrillated cellulose, or cellulose nanofibrils. They range in diameter between 5 and 15 nanometers. Right. So key word there is nano. You're at the nanoscale. Lengths can be upwards of greater than 1 micron. Now, the NFC that you all make in the lab is going to be in the range of about 100 to 300 nanometers or in length, so about 0.2 to 0.4 microns roughly. Okay. Crystalline nanocellulose, you compare the NFC to CNC, you can see that the ranges and diameters overlap. It's 2 to 20 nanometers, but the lengths are quite a bit shorter. Okay. When you get into NFC and CNCs, what it breaks down to is then you have to have a third aspect, and that's the crystallinity, and I'll talk about that in some upcoming slides. Right now, I just want you to focus on the diameter and the length. So the more, I'll call it the morphological structural characteristics here. MFC, microfibrillated cellulose, okay, is in the 10 to 15 micron diameter range. It's a lot larger, and 10 to 50 microns in length. So again, much larger. And if you look at the diagram on the right-hand side here, I've got kind of these images I think are a lot better to illustrate. You can see the trachea there, the wood cell, width of 20 to 30 microns in that image. I've found them to be about 10 to 50 microns. It's actually a bigger barn door. The length, 1 to 3 millimeters, depending on whether it's a non-wood or a softwood, right? So then if you look at the fiber surface, you see those fibril bundles. All right, you've been introduced to a little bit to refining. As you refine, you break the fibrils off the fiber, increase the surface area. Those fibrils are the microfibrillated cellulose. Okay, they're the ones that have the width or diameter between 10 and 50 microns. Dive a little bit down and see what those are produced or constructed from, and that's when you get into nanofibril. So you see that diagram there. It's kind of the little squiggly part is to indicate the amorphous region in the nanofibril. Everybody is familiar with that cellulose chain on the right-hand side there? You can nod if you are. I hope you should be. So I like this drawing because it really puts it in perspective. When you're talking about a nanofibril, and you look at the width of a cellulose chain, the width is only 0.4 nanometers, right? If I recall, the diameter I said you guys would be making is in the range of 2.5 to 5 nanometers. So how many cellulose chains packed into that crystal lattice is that? Not a lot, right? So I want you to get a feel for the size. So if an article that you read says, hey, I'm making nanofibrillated cellulose, and they're in the 10 to 50 microns, do you think they're actually making nanofibrillated cellulose? Or is it they're really talking about macrofibrils? Okay. The other, and I didn't mention in this presentation, the other clue to look for is in microscopy. If they can claim they can see it with an SEM, then it is not nano. Even though you might think scanning electron microscopy, it's got to be at the nano size. And it is. The problem is when you do SEM, you have to coat the material with platinum. And they coated it 4 nanometers in thickness. I told you, you're going to be making fibers that are 2.5 to 4 nanometers. You cover it with another 2 to 4 nanometers, you're not going to see the fibers anymore, right? Everybody agrees with that? So that's another clue. If you look at the logic in the research paper, how are they viewing these materials? Okay. Any questions on that?
If I can ask the question, if I can ask the class a question. So, you already we're already talking about nanofibrillated cellulose, different types. Can all of us talk about characteristics of cellulose at this moment? So, something what you learned in 406, that would be very fantastic because, this is learning new stuff and revisiting what we learned so far. So anything about cellulose which you can tell me, that would be good from 406 or anything.
Hygroscopic. What the whole is, maybe I should say.
There's hydrogen bonding between the cellulose chains.
Excellent. Only hydrogen bonding or something else?
There's like van der Waals forces too. There's other
Okay, is it
as well.
one or two or many, many, many?
There's many different
Excellent.
courses.
Mm-hmm. And in terms of, is it the homopolymer or heteropolymer?
Homopolymer, right?
Excellent.
Glucose.
Right. What kind of bonds we have in cellulose? Alpha 104.
Glycosidic.
It's beta 1,4-glycosidic because alpha is for the starch.
Excellent. All right. So
Potatoes.
we're getting sour. So we're warming up here. I'm like the usual, the warm up at here for this class. Okay. So another thing is, so Kurt mentioned about crystalline and amorphous regions. So what can you tell me about crystalline amorphous regions in cellulose?
Amorphous regions are much more easier to dissolve.
Excellent. And crystalline, right? This is tough. And that's why, you know, when you do more of this treatment, chemical treatment, then, you know, amorphous is going to go first, crystalline is going to stay. Excellent. So now we know everything about cellulose. I'm not even talking about cellulose 1 or cellulose 2 or 3 or 4, because that would be, you know, that would be stretching our imagination here. Right. But then again, this is so, it's something, you know, we obviously went all the way to the chain level. Now you're going to have few chains at the time. So I just want to put everything in perspective here. All right. Thank you.
All right. So what's important about nanofibers? So there's a lot of things we also specify, right, besides size. So I mentioned a little bit about surface charge, so chemical features as well as morphological. Now, have you guys started your literature review yet? Yeah. Yes, of course you have, right? So you've started reading it. As you dive into these articles, you're going to come across surface charge, and it's going to be in the range of 0.3 to 1.6, 1.5 millimoles per gram of carboxylic acid. That is, again, another clue that indicates you've got a chemical treatment versus a mechanical treatment. If you do mechanical treatment, you're not changing any of the surface charge. You're not adding surface charge. You can only do that with chemical means. Same with crystallinity. So I already mentioned that. You'll see crystallinity in the range of 45% to 94%. And this honestly is an entirely other lecture. If you want to get me on my soapbox, I'll talk about crystallinity until you are bored to tears. But 45% would indicate what? Chemical or mechanical? Anybody?
Would be mechanical.
Mechanical, right?
It's more broken down.
Yeah. And so this range has to do a lot with just some of the issues with the way crystallinity is calculated. So I want you to understand that as you read a paper, if it talks about the crystallinity, you're going to end up with ranges of crystallinity for crystalline nanocellulose, ranges for NFC or nanofibrillary cellulose that overlap. Really, those numbers are only good for comparing the data within that research paper. They're not as good for comparing between papers, okay, or between labs. So I just want you to understand, if you find a paper that says 82% and they call it CNC, and another paper says 85% and calls it NFC, it's likely an issue with how they do it's relative to that lab, okay? But the second thing is aspect ratio. So presumably you've heard this a lot, you know, your length divided by diameter. So NFC, the aspect ratio is typically 10 to 100. The NFC that you guys will be producing in this lab will be between 50 and 80, okay, roughly. Crystalline nanocellulose, right? The amorphous regions are completely gone. Its aspect ratio is in the 5 to 30 range. So that's another way of highlighting, is it CNC or is it NFC? Now, physical properties are also specified. Young's modulus is how tough or elastic the material is. So if you look at a stress strain curve, you're all familiar with that. The elastic modulus is that point before you get beyond the plastic region there. Okay, so the elastic modulus for NFC and CNC is quite high, 65 to 85 joules per gram. To compare that to steel, you can see steel is only 24 joules per gram. This makes this material very attractive for use in composites. Okay. The other thing it also has is a low coefficient of thermal expansion. So that means that it, under temperature, it's not going to change a lot, which when you're in composites, one of the big challenges in a composite material is if you have one material that has thermal expansion greater than the other, you end up, as the temperature increases, the material actually comes apart, and you don't want that. So another piece that's attractive to this. Other features are it's dimensionally stable. Okay, it doesn't change size. You're not going to continue to break it down unless you deal with it mechanically or chemically. It's optically transparent. Okay, it's biodegradable, right? Because it's already, and it's also, one thing I don't mention, it's also biocompatible with other cellulose. It's a cellulose product. So if you're looking at other composites that are based on biomass, you've got a nice a material that you can kind of plug in. And last, it's low weight. If you think of steel, steel's pretty heavy material. This is a low weight material. So if you add it to your composites, you're potentially not adding a tremendous amount of weight, right? And that can be cost. Okay. Any other things, Renata, that you can think of that I may have missed here that are specific for NFC? I know I didn't get everything here.
The reason why Kurt is doing this because you're going to be doing the literature review, which is due, I will send, if I recall, it's next Friday. We want to make sure you have, when you read the papers, and Kurt is actually at the bottom of each slide, he's adding this information, where did he got this material, right? So this is in terms of literature review. So it would be good for you to actually go and take a look at this stuff, because you have to write something, but you can write 150 million pages about nanofibrillate cellulose, don't get me wrong, but just so you pick just the important part. So this is in order for you to get the feel for it, because you're not, obviously, we didn't talk much about this in your junior year or even in your sophomore year. So we want to make sure you have enough information to start understanding what you're reading and give us the important information in the literature review, because that's what it is. You give us an essence, right? Not 100 million pages about nanofibrillate cellulose, because,
Yeah, I did post two reading articles to get you guys kind of started. Both are kind of nanocellulose reviews. But they have a lot of information there, and if you dig through their citations, that's where you're going to find some of the meat. You can really dive down. But I wanted to get you started out there, because you type in nanofibrillate cellulose, you're going to get 1,000 papers, and it's really hard to kind of filter those. So take a look at those two articles I posted. That should get you started and kind of get you a little more focused, so you can kind of be more efficient in your literature review. All right, so what can you do with this stuff? If you haven't figured out, Renata and I are pretty excited about this material. It is really cool. You can use it in packaging and paper material as a barrier coating. It reduces the permeability of paper if you add it, and that's a big deal in food packaging, right? Because you want to preserve. But typically now, food packaging, you deal with plastics and coatings that are not biodegradable. So if you recall, nanocellulose is a biodegradable material, right? It's got high strength. It actually increases significantly the strength of your packaging. It's used in medical wound care, tissue restoration. This image in C there is an ear, if you can't figure it out. It's not that they're going to stick that in your head, but it's to grow skin over the top of it, right? So it's a biocompatible material. Composite materials, extrusions, and D there, that's an extruded product using nanofibrillate as a reinforcing agent. And again, if you remember, thermal conductivity is really low. So for extrusions occur at high temperatures. So you want something that's going to be thermally stable, right? So it makes a good opportunity to displace expensive components. And it also offers that high Young's modulus. Electronics, it's used in electronics for conductive sensors. You've all heard about the smart paper that Anthony's lab is developing, right? That's an opportunity for NFC to be used in those products. Coatings as a reinforcing agent in coatings. NFC, again, I'm getting ahead of myself a little bit. We'll talk about the surface parameters, but you can use it to stabilize the rheology of your mixture. You can produce really stable colloids. And have you guys ever opened up a gallon of paint after it's been sitting for half a year? What happens to it?
All the liquids at the top and the paint particles are at the bottom.
Everything settles out, right? So if you have something that produces a stable colloid, has a stable rheology, what would that do to the paints, right? Now you're going to potentially keep all that material in solution as opposed to getting it played out. You're going to get more effective coating. Maybe you have to be able to use less paint, right? Again, this isn't all encompassing. There's a lot of different applications. This is just a few. Okay. Renata.
I'm gonna add something to it. Remember in 406 we talked about that 1/3 of our food is wasted, and because it's just the packaging. I mean, it's not saying the packaging. We buy too much, right? That's given, right? But then during transportation, we had the whole discussion series about this, right? So this is, coming up with smart packages. Some of the groups were coming up with a solution. So this is what we're doing. We're trying to use this material for smart packaging, so we don't have to waste this food. Right now, you've heard how expensive it is. So that's why Kurt is working on it. My group is working on it. Anthony's group is working on it. Rick is working on it to make it cheaper. Although we will want to profit more, right? I mean, we want to, pocket the difference. I'm joking right now. This is not what we want to do. But what we're trying to do, make it cheaper, so it's not going to cost, $30 or $40 a gram, right? So we can include this material in the packaging, so then we don't have to waste food, right? So that's quite simple. But you connecting the dots. It's not just because we want to make it ship, Amazon boxes, T-shirts, right? This is not about T-shirts. It's about saving the water, thinking about food, and so we won't waste it. Okay.
Yeah, definitely. Any questions or comments from you guys?
What makes it so that it doesn't degrade? Like, for example, that medical device, the ear, or like in coatings or kind of in things in general that you wouldn't want in general, because it's a good thing in some scenarios that it biodegrades, but it seems like it would act similarly to a plastic in some scenarios. But do you understand my question?
I think so. Yeah, I mean, it's going to degrade. Everything has a life expectancy, right? If you look at old newspapers, they're white for the first few weeks. If you take an old newspaper, you'll find that they've all the color has changed, right? And that's just because there's lignin in there. It's photoactive. It starts to break back down, right? It starts to turn brown. But as long as it is durable enough to last the lifetime of the product, that's what we care about, right? If you think of paper products, they're pretty durable. Cellulose will last a long time in the environment, but like anything, you do have to consider its application. What's it going to be used for? Any of you guys go to get fast food ever? Right? What do you get? You get your hamburger in a paper box. What's the lifespan of that paper box? It's usable life.
Just
15 minutes.
Eat it.
Yeah, what a waste. I don't know about you guys. I hate it. Knowing that all the energy and effort that went into making this paper box only to hold my hamburger, which I'm going to then throw in the garbage. If I was eating at McDonald's. I don't eat McDonald's. Right? So you have to consider that. And so I think it's a good question, Ryan. For this ear, for example, it just has to last long enough for the skin to form over it. But you'll find that the nanofibrillary cellulose is pretty durable material. It's not going to break down. I mean, eventually, I suppose UV and microorganisms will eat it. I'm not strong in the biology side, so I'm not sure. Renata, what eats cellulose? I know there's a bunch of enzymes and bacteria that will eat it.
Let's see what eats cellulose. I mean, no, this is 406 class. Let's
Besides cows.
A quick question. So this is, there are some funguses, right? They will be eating cellulose by itself first, right? So then gonna be chomping on it, right? So there will be microorganisms, funguses, they're gonna be degrading. You have a white rod, you have a brown rod. It depends really what's, that after, at the end, they'll go after cellulose, no matter what kind of material you're talking about. So there will be funguses going after. But if you wanna degrade the cellulose, once the lifetime of the product is over, right? And we want to just make sure we're not going to just keep piling, in the landfill or something like that. So we come up with the conditions, and we can degrade this material, right? Plastic, I mean, sure, you can come up with the conditions, but it's going to be chemicals, or it's by itself, it's not going to happen. And here we can introduce some little funguses here and there, and you're going to start chomping on cellulose. That's fine, unless we coat this material to death. And that's not gonna, obviously, the fungus cannot enter the cellulose chain, right? So it really depends what you wanna do at the end. And like Kurt mentioned, how long you want this product to last, right? So obviously, if you start painting, you wanna make sure this, after a week, you're not gonna have a holes in your, you're painting, oh my God, the cellulose is gone because, white rod or brown rod was chomping on your wall, right? So this depends always on the application, but it's yeah.
Yeah, interesting. You make a interesting question, but here's another thing. So I don't have it here because my nephew took his guitar with him, but we made a guitar a couple summers ago, and the coating that I use is a product called Nanocellulose, and it's a cellulose product, it's just nitrated, and it creates a lacquer-like coating. We sprayed it about 15 coats. And that's typically what are used on electric guitars in today's world. I don't use them on my acoustic guitars that I make, but I do use it on that material. It's a cellulose-based material, and it will last the lifespan of that guitar. Any guitar you see out there, most are coated in nitrocellulose. Okay, so good question. All right, so just where is it all made? Here's a list. This is 2015 list, so there may be some new folks that have been added to the list, but it gives you an idea of who's out there making it, and their capacities. And if you see one theme there, Scandinavia is definitely dominating this industry right now. Okay, Americans or North America, we're a little bit behind the gun on this, so it's mostly the Swedes and the Finns. Okay, so let's talk about oxidation chemistry, what makes it green, and specifically the chemistry that you guys are going to be using in the lab. So if you look at what you guys are doing this week, okay, you're going to pulp up your fibers, you're delidifying that fiber, right? You're separating the lignin, you're going to consume the hemicelluloses in there, and you'll end up with this delinified fiber bundles. You may have some hemicelluloses left over, not a lot. You're going to oxidize it. You're going to still have fiber bundles. Why is that? Pulp in, still going to be pulp out. It's going to look the same. Somebody mentioned it already today. What's happening between those fibers? You have a couple different types of bonds, right? We have a bunch of tools in our toolbox. So how are we going to break those bonds? Anybody?
Well, are you saying that we're gonna break the hydrogen bonds, but there's still gonna be van der Waals forces holding it
Exactly.
together?
Yeah. So when you add your green oxidation, you go from delinified pulp to oxidized pulp. You've broken the hydrogen bonds, but you still have van der Waals forces there. And so now we have to add some mechanical energy. And that at that point, then you'll have separated those fibers that you produced. Okay. So this is just kind of a high level overview. This green oxidant, you'll end up with, well, it occurs at a very low pH. So as you guys dig into your literature review and see the different chemical approaches, you're going to find tempo, you're going to find sulfuric acid, you might find periodate. All of these things occur at really low pH, right? So what does low pH do? Acid hydrolysis, right? It's going to attack your amorphous regions. Okay. When you're done with the chemistry, though, in this lab, you'll end up with an ammonium containing salt, your spent liquor. Okay, you might even smell a little ammonia left over. Okay, well, I want to talk a little bit about what do you guys think that makes it green, though? Why am I calling it a green chemical? What is green chemistry? If I say it often enough, it becomes fact, which sometimes happens.
You can reuse the chemicals afterwards.
You can potentially reuse the chemicals. Now, I haven't dug into I shouldn't say. I've done it once. I just haven't taken that research very far. But yeah, potentially you can reuse the chemical. Okay. A hint there. What's ammonia used for in agriculture?
Fertilizer.
Fertilizer. So I potentially use the spent liquor as a fertilizer, right? So the EPA, I was curious because everything in the literature I read about this oxidant called it a green chemistry, but nobody explained why they called it green. Because I mean, if you think about the entire life cycle of a product, you have to include how it's made too. And I was imagining this strip mine somewhere in Africa or India, big pit and all this, waste. And then it gets to me and I call it green, right? So green chemistry requires you to look at the entire design of the chemical product, the process, everything. And the idea is that it has to reduce or eliminate the use or generation of hazardous substances. And that's all the way from the opening of the gate to the end of the gate, meaning when you make your oxidant to the end of its life, okay? And so that's why I looked into. So green chemistry prevents pollution. It applies to all areas of chemistry. It applies to any innovation, right? Because you're trying to hopefully solve environmental problems, not create environmental problems. It results in the reduction of environmental hazards, right? Or the production. It reduces the negative impact of chemical products. So you could have a green chemical that maybe it's not 100%, but if it's the net difference is it's getting us in the right direction, you can call it green, although we just expanded the barn door, right? So that's a good segue into it. Lessens and sometimes eliminates the hazards from the existing product and process. So it's step changes, right? We're not looking for a complete touchdown or a complete score at the end, but we'll accept step changes in the direction of environmental improvement. And then chemical products and processes that reduce their intrinsic hazard. These are the things the EPA defines as, if you can satisfy one of these things or all of them, you can consider yourself green, okay? Any questions on that? All right, so the reaction chemistry you guys are going to be using, it breaks, it's activated by temperature. So once you've added it to your fibers, it's not going to do anything until you activate it. And so you start heating it up. So once you heat it up, it breaks down into two different reactive products. One of those products is generates the oxidation reactions, and that's what's breaking the hydrogen bonds between the fibers. The second product that's formed, and the kinetics of these, they form pretty much at the same time, focuses on the hydrolysis of the amorphous regions. So how do you control two competing reactions? Anybody know how to do that?
You could favor one with like activation energy if they have different activation energies.
Yeah, I mean, essentially you take advantage of your concentration of chemistry, your temperature, and your time, right? Before I started my investigation, I didn't know what my controls were, and I'll talk about what controls you have, because I want you to think about these things, okay? So again, oxidation breaks the hydrogen bonds, the hydrolysis attacks the amorphous regions, right? So you end up with depolymerization. And by controlling time, temperature, and applied chemistry, you can control the extent of those reactions. So let's talk about the oxidation first here. So everybody recognizes this molecule on the left. Is it clear? It's clear on my screen. I was hoping it would be clear on Canvas as well. My color choices, I didn't have a lot of selection. So can you see that? That's the cellulose. You all recognize that as the base cellulose chain or unit? Yes. All right. So add your oxidizer, temperature and time. It attacks the C6 hydroxyl preferentially. It doesn't attack C2 or C3. Okay. Now I only indicate one of those. You see it in yellow, it's carboxylic acid. Isn't there in the silibiosine, isn't there two C6 carbons, one on the other chain? Anybody know why it's not getting attacked? No?
Would it be sterics?
Sterics, yeah, right. It's think of the steric hindrance of your molecule, right? You don't have a perfect chain where all the C6s are playing up. It rotates around that oxygen, right? So some of those C6s are going to be facing down into the polymer chain, and they're going to be inaccessible. Okay, so typically this reaction, that's one reason you only get about 1.5 to 1.6 millimoles max. If you were to calculate out, and I can't remember what the number is off the top of my head, theoretically you should get a lot more because there's a lot more C6 hydroxyls there. But you're only attacking the surface of the nanofibrillary cellulose. Okay, does that make sense? So who cares? Why do we care? Right. So the big deal when you're making composites or designing a nanocellulose, when you do chemical means, you're going to activate. You're basically activating the surface of that chemistry. If you convert to carboxylic acid and you say I'm going to maximize, then you can actually lead into other chemistries. So we can convert that carboxylic acid into an ester. You should have had this in your organic chemistry courses, Fischer esterification. It's that wonderful SN2 reaction. Okay, you can convert it to an amide, and there's the current or one of the most popular compounds for doing this is N-hydroxylsuccinimidyl ester formation. So these are all precursors to use in other applications. So now you're changing the anionic cationic nature, you're changing the reactivity. You can actually add silanes to nanocellulose, and that is a step in creating, for example, aerogels that can absorb pollutants, right? You don't want an aerogel to absorb water. You want it to absorb nonpolar substances, right? So how do you make your nanofibrillary cellulose nonpolar? If you remember from organic chemistry, likes dissolve likes, right? Well, these are the steps, and that's why it's important for you guys to understand that what you're doing is you're potentially activating it. You're also developing electrostatic repulsions, right? And so you may be forming a stable colloid, but once you throw it in with paper, what's going to happen? If you're going to, because you guys are making security paper, so if you have a high charge molecule or nanofibrillary cellulose, how is it going to react with the fibers in cellulose? Is it going to repel them, or is it going to bond? Does that make sense? So these are things you need to think about when you are determining what conditions you're going to treat your wheat straw with. All right, so any questions there before I dive into the last portion of this? Going once. All right, we're almost out of time. So this is the oxidation process, kind of in a nutshell, what you guys are going to do. So on the left, we'll probably do it a beaker, not necessarily an Erlenmeyer flask. You'll put your fiber in there, add your, you'll take your ammonium persulfate or your oxidant, you'll heat it up to top temperature, whether it's 60, 70, or 80 degrees. You'll add your fiber to it. Duration of the time when you're done, we'll filtrate it. Now dialysis, I'll take over. You'll hand me your fiber, because that takes 4 to 7 days, and I'll return your fiber with dialysis complete. Dialysis takes out any remaining salts from your fiber. Okay, it's going to separate those things. So if you remember, I said there was ammonia left over in the spent liquor. We don't want any chemicals contaminating your fiber. Otherwise, those chemicals can potentially act as contaminants in future treatments, right? So if we add in it, you're going to be decorating your fibers with dyes, a fluorescent dye. We don't want anything that can impede with that, okay? So the next step normally is carboxylic acid. And the next slide, you'll see that you guys are going to calculate what that is theoretically. Then it comes to our mechanical treatment, because you still have, even after all these steps, you still have fiber. You haven't broken those van der Waals forces. So either ultrasonic or microfluidization, right? Then it's available for analysis. As much as it would be nice for you guys to be able to do some of these things, AFM and XRD are done at the MAF on campus, the molecular analysis facility. So what I will do is I will provide you with scans of NFC fibers and teach you how to use a freebie program called ProFilm to determine what the fiber diameters that you produced are. Okay, so that's kind of a quick nutshell of the process and what it will be like. Let's see. Okay, so nanocellulose response. So this gets back to that question of how you control the material. With aspect ratio, it is only affected by your applied chemistry and temperature. Time doesn't play much of a role in it. And there's a small interaction at the 90% confidence level between APS and time, but it's pretty small. We're not talking about significant changes in aspect ratio, right? So that tells you that there's probably some interference, right, in how this chemistry gets to the reaction sites. So likely it's probably a pretty fast reaction, right? It gets there, it's a small molecule, and so additional time is not going to help us, but applied and temperature. For surface charge, though, on the other hand, this is your chemistry. Applied, time, and temperature all play a role, strong role. Okay, so how are you guys going to determine what combination of levels and what are your boundaries going to be to get the aspect ratio you want and get the surface charge you want? Okay, these are the things you have to think about. So here's the ranges. And again, we're still a little bit behind what the dates we're going to be doing these NFC oxidations. But here are the ranges that I want your groups to use. Remember, we're limited to 4 hours in the lab. These ugly equations are the equation that you plug those values in, and you'll get to your carboxylic acid and your aspect ratio. Okay. And then if you want to calculate your length, you can back that out. Once you got aspect ratio, you can take your diameters from your analysis and solve for length. Okay. Any questions on that? And you have to memorize this equation, right?
Yeah, to pass this class, right? That's what usually we ask you for.
It's an